Good day. So, this is again your teacher, and here's our topic in General Physics 1. Hope this video will help you understand the motion of objects in one dimension. So, first we have mechanics. This area of physics is concerned with the motion of objects such as rocks, balloons, cars, etc. And to understand this branch of physics, we must be able to answer two questions. First, what causes motion? What is the cause, or what is the reason why an object or something is moving? How will an object move? So that's another question. In this chapter, we introduce a number of quantities, including displacement, velocity, and acceleration, that are essential for describing motion. We consider motion in one dimension, that is, motion along a straight line. So in this study, we are going to deal with objects moving horizontally, like cars, motorcycles, bicycles, people walking or running, etc. But first, what is motion? We can actually easily define or describe this word with our own understanding. It is the use of movement or a natural event that involves a change in position or location of something. It is definitely a state of change. But now, we first go back to its history. The word kinematics or kinetics comes from a Greek term "kine" meaning motion, and is related to other words such as kinesiology, which is the study of human motion. Kinematics describes how objects move, while dynamics deals with force and why objects move as they do. So just like mechanics, dynamics is another branch of physics. Now let's discuss each of the above mentioned important quantities in studying motion. First, we have time. Time is change or the interval over which change occurs. It is impossible to know that time has passed unless something changes. It's like the popular saying, time is gold. We treat time so important since nobody in this world could ever turn back time, and time itself is change. So we can stop it. So probably because time is change, we cannot stop the fact that some people will also change. So for time, we can make use of this formula. That triangle means delta, or that delta symbol always means change in. So we can say it's change in time is equal to TF minus TO, where TF is the time at the end of motion or the final time, minus T sub O, the time at the beginning of motion or the initial time. Though in some resources or some books, they use TI in TO instead of TO, but in this study we have to be consistent, so to avoid confusion we have to use T sub O as our initial time and T sub F as our final time. And the unit of time, as we have already discussed in our study in fundamental of physical quantities, the base unit of time is always second. Now, distance versus displacement. Distance is defined to be the magnitude or size of displacement between two positions. It has no direction and thus no sign. Is an example of a scalar quantity since it has no direction and its unit is in meters. While displacement is the change in position of an object, implies that an object has moved or has been displaced. It is also an example of a vector quantity. Now let's discuss what really is the difference between the two besides that distance is a scalar quantity and displacement is a vector quantity. So for example, distance between Midsayap to Cebu, which could take which could be miles away. So technically it's the difference between 2 points. Distance is the difference between 2 points. We're very familiar with the word distance. Whenever we hear this word, I can think of, whenever I hear this word, I can think of how far something has traveled. So that's distance. Another is displacement. For example, a person standing 3 meters away from a tree and starting to walk 1 meter towards the tree. That's direction. Another example for displacement. If Maggie is, let's say Maggie is walking 5 meters towards east. That means east means towards right. And turns on the other direction towards 2 meters towards west. The distance, if we're going to talk about distance, the distance traveled by Maggie is 5 plus 2 meters is equal to 7 meters. That's the total distance. However, if it's displacement, 3 meters, since displacement is the difference between 2 points, so the final position is that means the final position minus the initial position. So we have the answer for displacement is 3 meters only. So 5 minus 2 is equal to 3 meters. Because displacement has direction while distance doesn't have direction. Because distance is scalar quantity and displacement is a vector quantity. And you should always keep in mind that distance is always positive since it has no direction, while displacement can either be positive or negative because it has direction. Negative sign and positive sign displacement could mean either it's right or towards upward, towards left or downward. But since we're talking about one-dimensional motion or cars or motorcycles, bicycles, so either right or left. Now next, so for distance and um, displacement, we can make use of this formula, and let's say the variable we're going to use is x for distance. So change, since delta symbol always means change in, so we can say that this is change in x, which is equal to the final position minus the initial position. And the unit, of course, the base unit is in meters. Now, we have also here speed versus velocity. Speed is defined as the rate at which an object covers distance, and it's a scalar quantity. Of course, it also answers the question how fast this horse is running. So that's speed. So for velocity, speed with respect to time as a unit of distance divided by time, such as miles per hour or kilometer per hour. It is an example of vector quantities, just like distance and displacements. Speed and velocity also differs because the other one is scalar quantity and the other one is a vector quantity. But what do you mean by speed? When we say meters per hour, meter per second, for example, 10 meter per second. What do you mean by that? That means in every 1 second, you can cover a distance of 10 meters. So that's how you understand speed. And we usually hear speed when we travel from one place to another using motorcycles or car. So also speed can be visible along the road, national highways, kilometer post, and or cities where there's a speed limit and you have to minimize your speed because there's traffic enforcers who's monitoring your speed, so you have to follow the rules. So speed is applicable in those situations. Okay, next. So for speed, before I forgot, the formula is V is equal to X over T, where V is velocity or speed, X is the distance in meters, and T for time. So the unit will be in meter per second. Another is average velocity. It is displacement or change in position divided by time of travel. And for average velocity, we can make use of this formula where the the bar, the symbol for average velocity is this one, and indicated by the bar over V, that means average. So and formula is equal to change in position divided by change in time. So we can make use of this formula in finding average velocity, and its unit is in meter per second also. Instantaneous velocity is the average velocity specific instant in time. For example, when you are traveling from Midsayaf to Kidapawan, you started traveling at 6 a.m. to 7:30, and I would ask for your car speed or velocity during 6:42 a.m. That means at a particular instant, what is your instantaneous velocity? Another example is when a traffic enforcer holds a speedometer and caught a car exceeding to the speed limit. So the record on the speedometer is the instantaneous velocity of that car. That's another example of instantaneous velocity from the word instant. Another important quantity we have to discuss is acceleration. I'm sure you are all familiar with this word. It is a vector in the same direction as the change in velocity. It is therefore a change in either speed or direction. So if there's a constant change in direction, we can say that it's acceleration. If there's a change in speed, or if there's constant change in speed, that's acceleration, and its unit is meter per second squared. Just like a very good example of this acceleration is gravity. But we're going to discuss more about it later when we discuss vertical motion. Now, let us note also that before deceleration, I have to first give you an example. I'm sure everyone could relate to this example, since I believe all of us who have experienced riding a motorcycle. A perfect example of acceleration is when a motorcycle or a car is overtaking. Because when you overtake, you are speeding up. When a motorcycle, another is when a motorcycle is climbing uphill, you're also speeding up. So whenever a motorcycle, a car, or bicycle is speeding up, that's an example of acceleration. They tend to accelerate. On the other hand, just like when a motorcycle or a car is about to stop, when an object slows down, its acceleration is opposite to the direction of its motion. This is known as deceleration. Deceleration when an object slows down. So, for example, when a car or motorcycle or a bicycle is moving downhill, that's deceleration because it tends to slow down. So the opposite to the direction of its motion, we call that deceleration. Instantaneous acceleration. So the same concept with the instantaneous velocity that I have explained to you a while ago. The acceleration at a specific instant in time and is obtained by the same process as velocity. Uniform motion. From the word uniform, no change in velocity and speed. Acceleration is zero. You have constant velocity and speed. So from the word uniform, this could also mean that the motion of the object is constant, consistent, or unvarying. For example, when you travel from Southern to Notre Dame at a speed of 3 meters per second on a motorcycle, that's an example of uniform motion. From Southern, you started with 3 meters per second, then you didn't change your speed until you reach Notre Dame. That is an example of constant or uniform motion or constant velocity. Now, question is it possible to have a constant speed when traveling along a curved path? Maybe you would answer, it would depend on how curved the path is. Of course, it is possible. If it's sharp, of course, you cannot remain at constant speed. You will tend to slow down if the curved path is too sharp. But sometimes, if it's not too sharp or the curve is too quite long, you can have a constant speed. Is it possible uphill or downhill? Certainly not, because when you go uphill, you have to speed up, and downhill, you have to slow down. So there's no uniform motion when you ride uphill or downhill. Uniform motion of cars or motorcycles or constant speed is only possible along a straight path without any obstacles. Maybe it's possible to travel at constant speed from Southern to Notre Dame early in the morning, like around 3 a.m., but not 9 a.m. to 4 p.m., unless the town is under the mandate of enhanced community quarantine, wherein there's no more Not the street is not busy. Now, before I give you the formulas in finding these important quantities, I need to show you first its derivation. It is important to show first the derivation so you won't ask anymore where these equations come from, right? Okay, so now let's have first the derivation of formulas. Of course, I brought with me my resources, my book. In the derivation of formulas, some formulas are given and some are obtained throughout the solution. So I hope I can explain it very well. So thank you for listening and for taking the time to try, listen, and understand this discussion. So let's first assume that these variables are, for example, change in time. Let the initial time, TO or initial time, be 0, so that our change in time is equal to the final time or just T, and change in position or distance is equal to x minus xo, and change in velocity is v minus vo, where we assume it's the final velocity and x is the final position. So solution, let's start with this average velocity, wherein average velocity is equal to the change in position divided by change in time. Since time t, our initial time is taken to be 0, so final time will remain at the denominator here, and we have this one, so just copy x minus the initial position. Next, we're going to solve for x from this equation. We have to solve for x, finding another equation for x. So we have to from here to here. What happened? Of course, multiplying both sides of the equation by t. So t here can be cancelled. If we're going to multiply t here, this t here will be cancelled, and t here, not changing the equation, we just had to introduce a variable t. So that's why we have t here. So bt is equal to x minus x sub o, since t here was eliminated. And solving for x, we just have to transpose this initial position to the other side of the equation. This becomes x sub o plus vt is equal to x. Since this is negative here, if we can transpose that to the other side of the equation, this becomes positive. So arranging the equation now, since the remaining variable here on the other side is x, we have to flip it. This becomes x is equal to initial position plus velocity times time. This could be our equation 1. So this is another equation in finding the displacement. Next, a from this equation of acceleration. Acceleration is equal to change in velocity divided by time. So not with respect with the this with displacement or position of the objects, but with respect to acceleration, velocity divided by time. Since TO is taken to be zero, the remaining variable at the denominator here is t. So A is equal to V minus VO over T. AT, what we're trying to solve here is for velocity. AT is equal to, what happened here? T transferred on the other side. Technically, that is because we introduced T on the other sides of the equation, not changing the expression, just to eliminate this T here, so that we can put T on the other side. So AT is equal to V minus VO. Solving for velocity, we have to transpose this VO on the other side, so this becomes positive, because since this is negative, so this becomes positive. VO plus AT is equal to V. So rearranging the equation, this becomes V is equal to VO plus AT. That's it. This will now be our equation 2. Another formula for velocity. If there is a given initial velocity, acceleration, and time, we can make use of this equation. And we have now to continue from this expression again. If we're going to continue solving so that we can have another formula, we introduce both on both sides of the equation VO. We have to add on both sides, so VO plus V is equal to VO plus VO plus AT. So what we add up is VO initial velocity and the other sides of the equation. So this becomes, since these two terms are the same, this becomes 2VO. So don't mind first the 2 here in the denominator of each expression. So this becomes VO plus V is equal to, since VO automatically, there's 1 here always, it's constant, we have 1. So 1 plus 1, since they have the same terms, this becomes 2VO plus AP. So to eliminate the 2 here, we have to introduce to each expression a denominator of 2. So 2, this becomes VO plus V over 2, and 2VO over 2 plus AT over 2. This will be eliminated. So this becomes, what happened here? This becomes average velocity. When we say average, if you have how many velocities here? We have two different velocity, and divided by their number, which is 2. That's average. That's why we have this average velocity here with a bar on top. Is equal to, this will be cancelled, so just 1. That's why we have 0 here, plus, since we still have 2 here, this becomes 1 half AT, or this expression and this one is just the same. I hope you still can remember how to do that. That's basic mathematics in your algebra. Do recall how to solve these kinds of equations, how to simplify equations. If you still can remember, you won't have any trouble understanding these derivational formulas. So this will be our equation 3. So we have 3 equations now. From equation 1, so let's go back. From here, x is equal to initial position plus average velocity times time. From that equation, we have 1, okay. We're going to derive this equation. Now let's x is equal to x initial position plus, we substitute from here since we got this in our equation 3, average velocity is equal to VO plus 1 half AT. We substitute this expression here. If we still could go back, you see this one, average velocity is equal to this expression. So what we did is substitute that expression in this formula. That's why we have this one. Do not forget this t, so copy that. So our x now is, then we have to distribute this t. So x is equal to initial position plus VO times time plus 1 half AT, since we have time here. This becomes times that times time is equal to t times t is t squared. So x times xo plus is equal to xo plus VOT plus 1 half AT squared. This is our equation 4. In case we have these given on a problem and the x is unknown, we can make use of this formula. So from equation 2, v is equal to vo plus at, deriving this formula to solve for time. Is it to solve for time? Yes. This VO here, since it's positive, we're going to transpose that on the other side of the equation. This becomes V minus VO is equal to AT. So to remain time in this side of the equation, we have to divide both sides of the equation by A, so that A here will be eliminated. This becomes T solving for time. Since a here will be eliminated, a will remain in this side of the equation, b minus vo over a. So t will remain in this side of the equation. And arranging this formula, this becomes t is equal to v minus vo over a, which is our equation 5 and can be very useful in finding time. So from equation 1 again, so we have many equations, and these equations can be very useful in solving problems later. So x is equal to xo plus vt from equation 1. If we're going to substitute the this average value, I forgot to put bar on top of it. So if we're going to substitute the value, the expression equivalent to this velocity, average velocity, which is when we say average, two different velocities, and divided by the 2. If there's three velocity, VO, V1, V2, that should be divided by 3. So that's what we call averaging. So x, of course, t here, copy, then let's distribute it inside. This becomes x. Let's transpose first the initial position on the other side of the equation, and this becomes, since it's positive, this becomes negative. So x minus x above is equal to vo plus v over 2 times time. So first, before distributing the time inside, we have to first substitute. I forgot, we have to first substitute equation 5, this one, on t. Okay, so here, since t is equal to this expression, let's substitute this one, v minus v over 8 here. So this is what's happened. X is equal to copy, is equal to VO plus V over 2 times the value of time, which is this one, V minus VO over A, or the expression equivalent to time. So this becomes multiplying these two expressions. X minus XO is equal to V times VO, VOV, V minus VO squared minus VO times VO negative VO squared plus V times V is V squared negative VO times V is negative VOV, since they are not the same, and just copy the negative sign since the other term is negative. So 2A divided by all divided by 2A. This becomes this one. So since these two expressions are, this is positive, this is negative, so just like 1 minus 1 becomes 0. So these two will be eliminated. So the remaining numerator will be negative VO squared plus V squared, or V squared minus VO squared. Okay, so X copy divided by 2A. Then to we have to multiply both sides of the equation. 2a, introducing 2a on both sides of the equation to eliminate this one here. So we have, since it will be eliminated because we introduce 2a multiplying on both sides, the remaining expression will be 2a times x minus x sub o is equal to, this will be eliminated. That's why we have these terms here, negative VO squared plus V squared. We have to solve for V squared now. V squared. To solve for V squared, we have to transpose this one. And since it's negative, this becomes positive on the other side of the equation. So VO squared, I automatically arrange the equation. So V squared, since this one will remain in this side, so it's just the same. V squared is equal to VO squared, this became positive, plus 2AX minus XO. Yes, X minus XO. So this will be our final equation, or our equation 6. So we have how many equations? 6 in all. We have derived with 6 equations. Thank you so much. Now, let's have examples. Example problem number 1. A particle moves 30 meters in 15 seconds. Determine the distance traveled in 5 minutes, and the time needed to travel 300 meters. Of course, it is very important to first identify what are the given in the problem and what are the unknown or required in the problem. What is asked? So given x, of course, since it is in meters, that means it's distance. So let's put x is equal to 30 meters. Given that the time is in 15 seconds. So required, first requirement, we have two sets of requirement. First, determine the distance. So x, if time is 5 minutes, and second, time needed, time if x is equal to 300 meters. Now let's solve for this problem. Solution. So for A, x is equal to Vt. We can make use of this simple formula since we have time given and x is given, so we solve for velocity, of course. It is necessary for us to solve for velocity because the only unknown here, x and t is given, x and t, we have conditions between x and t. The only thing that is unknown is velocity, so first we have to solve for velocity before solving for the x, or the position here, and the time. So first velocity is equal to x over t, or the position divided by time, distance divided by time. So distance is 30 meters divided by 15 seconds. So we have no further solution here. 30 divided by 15 is just 2, so 2 meters per second is the velocity of the particle. So since we have known the velocity, we can solve for letter A. What is the position or the distance if time is 5 minutes? So just use the velocity, which is 2 meters per second, times, since its time is in 5 minutes, we have to convert this back into its base unit, which is second, since our velocity is in meter per second. So 5 minutes times in 1 minute, there is 60 seconds. So minute here will be eliminated. Remaining unit is in seconds. So second here and second here will be also eliminated. Remaining unit now is in meters. When you solve problems, I just would like to remind you, do not forget to always put the unit. Sometimes some of my students will just put x is equal to 600 without putting the unit here. Always put the units. Okay, it's like the last name. And for B, since we already know the velocity, time is equal to x over v. So time is equal to, given that the distance is 300 meters, divided by velocity 2 meters per second, of course. Meters and meters here will be eliminated. So the remaining unit is second. So time is equal to 150 seconds. Another example. So these are the final answers. Find the average velocity of the train during the time interval between 3:14 p.m. So we have this given time here when the train is 3 kilometers east of the origin, and 3:56 p.m. when it is 26 kilometers west of the origin. You can actually plot this problem on a Cartesian plane, so you can it will help your imagination. And often when we solve problems, our imagination is very helpful, and our analysis, of course, we have to analyze the problems very carefully so that we will come up on a right solution. So what are given? We have change in position. So why do we have here negative 26? So since it's towards west of the origin, west is towards the left. So the negative sign here indicates the direction of the motion of objects. So we have to put negative 26 kilometers minus 3 kilometers, because 3 kilometers east. So the change in position, final position minus the initial position, is equal to negative 29 kilometers. We also have time, the final and the initial. Our initial is 3:14 p.m. and final time is 3:56 p.m. So in between minutes. And we are to solve for the velocity. Let's have first the conversion of unit, since it's in minutes, so time is equal to 56 minutes. The final time minus the initial time, which is 14 minutes, is equal to 42 minutes. Since it's in minutes, we have to convert that into hour. Since our distance is in kilometers, so kilometer per hour, so we have to convert that to hour instead of second. So 40 minutes times So in 1 hour we have 60 minutes, so that minutes here will be eliminated. So 42 times 1 divided by 60 is equal to 0.7 hours. Next, now that we have the time, we can now solve for our velocity. Average velocity is the change is equal to change in position or distance divided by time. So our distance is negative 29 kilometers divided by 0.7 hours. So kilometer per hour is the unit, and the answer is negative 41. Why negative? Because the negative here only indicates the direction of the motion, so it is towards west. Okay, another example. How far can Kendall Jenner, let's see if you know Kendall Jenner. Do you know Kendall Jenner? Are you watching fashion TV? How far can Kendall Jenner, anyways, how far can Kendall Jenner travel using a bicycle in 2.5 hours along a straight road if her, what's this? If her speed is 18 kilometers per hour. So given we have change in time is 2.5 hours and velocity is 18 kilometers per hour. How far? How far means we have to solve for the distance. Okay, so change in position is equal to, from the formula, x is equal to v times t. So 18 kilometers per hour times 2.5 hours. So hours will be eliminated. That's remaining unit now for distance is of course kilometers. Okay, another example. How long does it take a car to cross a 30-meter wide intersection after the light turns green if it accelerates from rest at a constant 2 meter per second squared? As you can see, this example can be tricky sometimes. Okay, can be tricky. Why? We have here acceleration from rest. It accelerates from rest. What do you mean by from rest? That means from zero. When we say from rest, zero, and it starts to accelerate at a constant 2 meters per second squared. So given, what are given in the problem? We have our distance, 30 meters, our acceleration, 2 meters per second squared, our initial position is zero, our initial velocity is zero. That's what we meant by from rest. And the requirement or what is asked in the problem is time, since it speaks about how long. So it's time. For its solution, we can make use of this equation since there are other variables involved in the problem. We cannot just ignore them because they are zero. So if we have initial position and initial velocity, we can have, though they are zero, we can make use of this formula. So to find time, we have to derive this formula so that the remaining variable on the other side of the equation is just t. So solving for time, we substitute the values of these two expressions. So 0, 0, since VO is 0 times time, 0 times times, it becomes 0 also. So the remaining expression here is just x is equal to 1 half at squared. Solving for time, we have to multiply on both sides of the equation of times 2, so that these two here will be eliminated. So 2x is equal to the remaining expression 80 squared. And a, we have to divide both sides of the equation a, so that a here will be eliminated. Again, this becomes 2x over a, and the remaining variable now here is t. Now what will happen to the squared? How to eliminate that square? We have to introduce a square root. So square root on both sides. The square here will be eliminated since it already has square. If we're going to put square root here, this will be eliminated. So the remaining is the square root in 2x over a. So square root of 2 times our x is 30 meters divided by a, which is 2 meters per second squared. So the final answer would be, simplifying this equation, the answer is 5.48 seconds. Last example. If you are driving 110 km per hour along a straight road and you look to the side for 2 seconds, how far do you travel during this inattentive period? How far? So it speaks about the distance. Now, what are given? Given is velocity first is 110 km per hour. Time is 2 seconds. We have to solve for x, so it's very simple. We just have to, first, since the time is in second, if you can observe, time is in second, velocity is kilometer per hour, so either of the two we have to convert. So velocity is 110 kilometers per hour. To eliminate kilometer, we have to put this same unit on the denominator. So in 1 kilometer, we have 1,000 meters. So these kilometers here will be eliminated. And in 1 hour, we have 3,600 seconds. To eliminate this r here, we have to put r on the numerator. So we can eliminate these units here. Remaining unit should be in seconds, so 3,600 seconds. This is 60 times 60, so 60 minutes and 60 seconds, so 3,600 seconds. So this becomes 110 times 1000 divided 1 times 1 divide 3600. The answer is 30.56 meter, since this is the remaining unit on the numerator, and second, the remaining unit on the denominator. Okay, so these units can be denoted. And now let's solve for the distance. X is equal to vt, where v is 30.56 meters per second and time is 2 seconds. The answer is 61 meters. So you've reached 61 meters for the 2 seconds that you look to the other side while driving. Okay, I think that's all. Thank you so much. If you have any queries or questions, you may message me through my social media accounts I provided. Thank you very much.